Hi, welcome to topic 12.4. So this is the last topic in unit 12. This is Ampere's law, and I do apologize, I forgot to animate this slide. So we'll just kind of go down it. So Ampere's law is important. So it relates the magnitude of the magnetic field to the current enclosed by an imaginary path that we call an Amperian loop. So its equivalent that we've already talked about is Gauss's law. Right, so Gauss's law, where we use the Gaussian surface to enclose charges. So now we're going to use a loop to enclose a circuit, or sorry, not a circuit, but a current. Okay, and so for Ampere's law, we're going to do the closed integral of b dot dl, or surface integral of b dot dl is going to equal, mu 0 I enclosed. Okay, very similar to Gauss's law, which was the E dot dA equal to epsilon naught over, or charge over epsilon naught. Okay, so Ampere's law can be used to determine the magnetic field near a long straight current carrying wire. Solenoids, so when we have multiple wires, or one wire turned into multiple curls, can be assumed to be a very long wire with uniform magnetic fields. And then with negligible outside fields. Ampere's law, we can use it to determine the inside. So for a solenoid, it's going to be mu 0 Ni. Okay, N is what is called turn density, right? If you want, so it's going to be turns of the solenoid per length, or capital N over L. So you can rewrite that equation to be, so for a solenoid would be mu 0 capital N I over L. Okay, it's just another version of that solenoid equation. An Amperian loop is a closed path around a current carrying conductor wire, which allows us to use, so now we get into the third of Ampere's law, or third of Maxwell's equations, which is actually the equation that Maxwell did contribute something to. So B dot dl, right? So we have Ampere's law is mu 0 naught times I, right? So that's Ampere's law. And then here's Maxwell's contribution, mu 0 epsilon naught I of d phi electricity dt. So so this right here, that is Maxwell's contribution to his equations, or his set of equations. Maxwell's contribution. Okay, so aside from putting them together, because Maxwell equations are just a way to explain light, and light is a combination of electric and magnetic fields. Okay, and so that's what that mu 0 epsilon naught d phi dt kind of does, is it brings in this combination piece. Okay, so let's look at an example. I actually almost forgot this example, so I had to kind of like just create this at the end. So we're going to use Ampere's law to derive the magnetic field for inside and outside of an infinite cylinder. Okay, so we need to make sure we define an Amperian loop, and we're going to assume all currents are distributed uniformly. Okay, so when we do outside the cylinder, our Amperian loop, right, is going to do something like this, right? And so if we're here in the middle, it's going to go out to a distance of, we'll call it lowercase r or capital R. Let's call it capital R. Okay, and then when we're inside, right, and so this will be, let's call this lowercase r, make it easier. So we have lowercase r, right? But remember that this will have, the cylinder will have a radius. So it's just like when we did inside the sphere, when we had to basically find the ratio of those r's. Okay, and so what we're going to do, start Ampere's law, B dot dl, Okay, and that's going to be equal to mu naught I. And so this is going to be part A. And here's the good thing. Don't be crazy. B dot dl is just going to be B times L. Well, we made a loop. That's a circle. So the length of that circle is going to be 2 pi r. Okay. And then we just simply now, right, solve for B. We're going to divide both sides by 2 pi r. And so the magnitude of the electric field around this cylinder is going to be mu naught I over 2 pi r. Okay, so this is outside the cylinder. That one's easy, right? Because we don't have to worry about what's happening inside. Okay, now when we go inside, we have some more steps we have to do. Okay, so we have current density is going to be equal to the current density times the area, right, of our loop is going to be equal to the current enclosed. All right, but J is I over pi r squared. Okay, and that's for the entire cylinder. The area of our loop is going to be pi times little r squared, and that's going to be I enclosed. And so we got a little bit of cleaning up we can do here. And so the current that we're looking for is going to be I apologize, yes, so we got it right. Okay, so this is going to be our I enclosed. And now we're going to do our B dot dl, integral of B dot dl. Mu naught I enclosed. Okay, so again, don't let it freak you out. That B dot dl is just going to be B times L. Mu 0 I enclosed. Well, L is going to be, again, 2 pi r. Okay, because now that's going to be our loop, right? The length of our loop, which was called lowercase r. And then we have mu 0 naught times our I enclosed, which is the current that goes through, times r squared over big R squared. Right, and then we can do, again, a little cleaning up here. Boom, boom, that goes away. And so the magnitude of the magnetic field that is inside the cylinder is going to simply be mu naught I times little r over 2 pi r squared. Okay. So here are our values, sorry, I just kind of looked like I just scribbled out that one there. So something to note that inside it has a linear dependence on the radius, but outside it has the inverse square. So you may get something, right, that looks, for this. And so if this is big R, so inside it's going to be linear, but then outside it's going to have this 1 over r squared relationship. So you have a linear relationship inside, 1 over r squared relationship outside. You probably will want to note that that graph. Okay, so that's unit 12, right? So it's a very quick unit. It lays the groundwork for a lot of what we're going to do in unit 13, which is electromagnetism. And that will be the last unit for AP Physics C, electricity and magnetism.